microwave resonators. This is going to go into some examples of how to convert between different components and the actual circuits, and make some connections between that and the microwave components you're building through Keysight and through Altium. So let's start off with, let's see if we can do this over here. What is a resonator? Okay, it's a very important question. Basically, all this means is that you're operating a component at the resonant frequency of the design. Now, we talked about resonant frequency last week, and we talked about how we calculate resonant frequency. And so each one of these circuit designs that you're making has a resonant frequency, either on its own or combined with other components. So you would have to do some calculations and figure out what that resonant frequency is. But essentially, that's what we're trying to work with when we're dealing with microwave components. So let's look at some quick examples, some quick conversions. And hopefully my handwriting will get better as I keep using this. This is in your textbook, page 205, and this I'm going to refer to figure 4.23 in your textbook. And so when we're talking about, say, a single trace, this being your PCB, and we have a trace coming in at some characteristic impedance, this directly translates into a circuit of a transmission line with some characteristic impedance attached to some capacitor. So that is the direct translation between the two. And so we can take this by circuit design and go to trace, or take our trace and build a circuit design. Either way works. The next one on this list, it happens to be two trace lines, both with equal characteristic impedances on a board, and each one has their own characteristic impedance with a capacitor. And then, so let's just do each of these independently, and you will see that both of these have capacitors attached to them, both with some characteristic impedance. But then, because these two are right next to each other, they have their own coupled capacitance. So this is CG and CP and CP. So we have three different capacitors by these two traces. Another form of this is, say, and this is very common, is having a board with a trace and a stepped impedance. Okay, so this has some Z01 in your textbook. They refer to this as Z01 and Z02. So two different characteristic impedances, 50, 75 ohms, 25, 50 ohms, doesn't really matter. But then this directly translates to this. In here, we have to treat this as an inductor with a capacitor and another inductor. So that is how this is treated. And we have both characteristic impedance here, Z01, Z02, and then we have both L, L, and C. So that is how these are translated between the two. We will see these more often. This is essentially, I mean, a symbol, or your first one is a example of kind of like a trace patch antenna. But it turns out to be a capacitor. We have our other capacitor, we have our stepped impedance. So this is what happens when we do stepped impedance. As you can see, when we do this sharp step, that's really where these capacitors come from. And then I am going to go through and I will erase this so we can work on another one. I will attempt to snip these videos together if I have the ability to, so you don't have to see me erase each time. I just don't know how to do that yet, so this will be a trial and error method on me. So the next step will be, hopefully you will never see this part if I learn how to edit these things properly, but if not, it's okay. The next one we will talk about is a split trace. And you can look at the figure for better drawings. My drawings are probably not that great. And we're just going to consider this 01, Z02, Z03, meaning they are separate impedances on each trace. Most of the time, this 2 and 3 will be identical because most of the time you want to split power between these two and you want to split power equally, but not always the case. So this is directly translated to, based on everything we've done so far, we have to assume that these are different steps also. So we have a transmission line coming in, and this is my Z01. This is attached to an inductor, so the inductance of that trace line. This goes out to another inductor for the second trace line, and that is my characteristic impedance, Z02. Okay, that's a Z. Apologize. My handwriting is terrible on this. And we usually draw this second line just solid almost all the way through because it is a reference plane. And then we will go out from here, and I will draw this from here and go over top of this line because I don't want it to cross. There's another inductor, and then this will come out to here. And then this is my Z03 transmission line. So I got all three of my transmission lines. I have 3 different inductors, but then I also have a capacitor connected to here. There's a ground plane underneath this that couples these 2 things together. And so then we end up with L1, doing Z, L2, L3, and this is how we build, and as you can see, this is the essential building blocks of a power divider. So this is how we build these things out from trace designs. The last one, and you'll see an example in your textbook about this one, mainly because even though we don't do this on a circuit board, anytime you add an SMA connector, you have a cylindrical transmission line going into a trace transmission line. So this last one is, here's your PCB with some copper pour on it, some design, whether it's this trace or something else. And we will label the Z0M, Z not M, so that is your trace line. And then we have a connector that's going through here, right? And then here is your coax line coming out. All right, so this is Z not C. For our designs and for what we're doing through the Keysight and the Altium designs, this is going to be an edge card, right? So an edge SMA connector that will solder directly to the top. The work is still the same. It doesn't change. The fact that it's going from the bottom versus the side really doesn't matter. So this translates to, you have a transmission line, Z not C, and we have it coupled with an inductor. These are directly connected, so that is an inductor. Then this comes out, and I'm going to leave the rest of this Z not M, and this is going to connect. But there's more to it than this, mainly because we have this cylindrical, this grounding shell here, and then we have all the capacitances between here or between this and your ground plane if you have a ground plane like that. And so we need to attach our capacitances between those two. Okay, so that fills in the rest of the options. There are more than this, obviously. These are just the main ones that we're working with right now. And so we'll label this C1 and C2 because these will not be equal. One's based on the capacitance of the cylindrical transmission line, one's based on the capacitance of your trace on your PCB. And then this is still L. Okay, so that's all the ones that are actually in the textbook for this particular section, but there are more. So the question is okay, so we have all these constructs and we have some physical design translated to some schematic that we can input into Keysight, do some simulations, take that, export it into a layout, do some trace calculations, put that into Altium. We can build these things. But we need to do some quick analysis in order to figure out if what we're doing is actually correct. So what are these actual values? How do we get the traces that we want? How do we design around all of this stuff? So let's start over from resonant circuit design. So we are going to talk about series and parallel resonant circuits. They behave very differently. Well, not very differently. I think they behave very similar. That just the math is a little, is the difference between series and parallel circuit design. So I'm going to draw this out. This is from your textbook, so figure 6.1. So we have a voltage source. Okay, so we have some voltage source, some connected into a circuit that has a resistance, an inductance, and a capacitance, right? And so we've all seen this type of stuff before, RLC circuit. Welcome back to PECA. We have some current going through this circuit and some voltage plus and minus. That would be a plus. And some impedance, input impedance that's going through this circuit. And for our output, we are definitely going to see some type of response. I may try to use some other colors. I just don't know how well it'll come up, but I'll give it a shot. So as you can see, let's start with, this is Zn, and this is as a function of frequency, rotational frequency for this case. And so we're going to put the absolute value in, so we're not dealing with negatives right now. And then this is going to, or normalized, I'm sorry, not absolute value, normalized. And then, so we're going to talk about how this curve behaves. So say we're sweeping through a omega over omega naught, so we want to normalize this to some type of normalization. That's why the omega naught's there. And so this way we get our center frequency as 1. Okay, this is why we normalize. Okay, at R, this would be here. This is the R value. That's where your characteristic, your Zn equals R. And then at R, somewhere around here, R over 0.707, okay? And that is right here, somewhere in that range. If you want to see a better picture, your textbook has it. So this here, and of course, I'll use the yellow one for the blue. I'll use blue for this one. In here, from here to here, this range from this point is your bandwidth, okay? More explicitly called half power bandwidth. So this is how we know exactly how much power is going to be distributed for each of, say, the feet in your power divider. Okay, apologize for the interruption. I just learned how to actually adjust the light sensors on this, so this looks great and the board looks much better. So I may end up re-recording some of the initial stuff again just to do this properly the first time, but now I can see everything. It looks so good on the video. I think we're going to keep this one. Okay, so let's get into this again. So we want to, let's say, calculate our input impedance. So from this circuit, again, this is nothing new. We have Z, my input, equals R plus J omega L minus, now you can write plus 1 over J omega C, but I write J minus 1 over omega C. And this is equation 6.1 from your textbook, just so you have it. We need to talk about how power, we want to look at the power delivered to the resonator. Okay, and this is going to be complex. Okay, so we're looking at Pn, so everything's looking at this input side, and this is just 1/2 VI complex conjugate. Okay, that gives me, we just did power last week, so this should be relatively fresh in your mind. Zn I squared, which equals 1/2 Zn V over Zn squared. Okay, and let's make sure I can write this correctly. There we go. Plugging that in, we already have some of this information, and then we are going to get, oh, not a touchscreen, sorry. 1/2 I squared. Okay, plugging in Zn, R plus J omega L minus 1 over J over omega C. So power, looking at this is the power going in. We need to distinguish the different types of power, whether it's reactive or dissipated by the resistor, or actually reactive power. So we're going to look at, if we want to just look at the power dissipated by that resistor only, that is just going to be our power loss, right? We don't get that back. We get the other power back from your inductor and your capacitor. So this is just 1/2 I squared R. So nothing crazy there. Looking at this again, we also need to distinguish between the magnetic and the electric energy that's being dissipated. So we're going to evaluate both my inductor and my capacitor in this. So when we're looking at this, we need the energy stored in the inductor, right? So we have energy stored in the inductor. Okay, that would definitely be just Wm 1/4 I squared L. Okay, let me see if I can clean that up. My handwriting's getting a little off from being down here. Magnetic energy 1/4 I squared L. Okay, and then my electric energy in the capacitor, that is 1/4 VC squared C, or 1/4 I squared 1 over omega squared C. So this is my magnetic, and electric. Okay, so this is for the inductor and that's for the capacitor. Okay, so that gives us all of the values we need in order to rewrite our complex power. In order to incorporate all of the different energies that we're dealing with, losses, really, it's all losses in our system. It's a little hard to wipe off sometimes. This. Yes, there we go. Okay. So now we can rewrite complex power as Pn equals my P loss, that's from my resistor, plus 2 omega J Wm minus We, so our power loss due to the electric and magnetic fields. Therefore, the input impedance then, Zin, is now rewritten as 2Pn over I squared. So adding this right in there, we can go through and actually add that this equation directly into that, which would be 2G. Okay, okay. All right. There it is. So we have our P loss, 2 times Pn. So we're going to, if you distribute this all the way through, we're just drop this down. Your textbook writes it the 1/2 down here. I'm not a huge fan of that, but we'll keep it consistent with your textbook. So this is just P loss plus 2 omega J Wm minus We over 1/2 I squared. So the question is, we started resonance. Okay, so resonance occurs when the average magnetic and electric energies are equal. So that's essentially where your resonance actually happens. So we're looking at, did I get this? This term right there. Okay, so we need, for resonance, we need Wm to equal We. Okay, so that's the condition that we're going to use. Therefore, your input impedance is now our P loss over 1/2 I squared, and then this is R. Okay, so purely real. This is a purely real term. Okay, the other thing that this implies, okay, is that omega naught is therefore equal to 1 over the square root of LC. So we recognize this from hopefully electronics and or PECA, but this has been a constant in all of your electronics classes. So the fact that we can actually pull that out of this shows that we're actually on the right path. Okay, and if we remember, we did this for a series circuit. So we need to actually go back and look at a parallel circuit in order to verify that these numbers are actually the same, or more importantly, how they differ. And the math is all basically the same. So we're going to start off with an equation or a circuit diagram and a plot and kind of build it out from there and see where we end up. Okay, a lot of the same, there we go. Same assumptions that we used for the first version of this for the series circuit are going to be the same assumptions we use for the next. So we're going to look at a parallel circuit. Okay. Now in your parallel circuit, we're going to look at, you have an frequency, voltage, plus and minus. We come out and we do some capacitor, some inductor, and some resistor. So we got some capacitor, some inductor, and some resistor. Okay, we're still looking for our input impedance, and I will write that a little better than that. Okay, and when we're looking at this, we have some current going through this and some voltage, and then this plot should look something like this. And instead of you get the dip, we're doing this in reverse, so it should look something like this. And then again, we're normalizing about the center, so that is my 1. Okay, so that's my normalization. So this is omega over omega naught. I'll write that better so you can see it. Omega over omega naught. Okay, and we have some max value here, and this is R value. That's where R is. So when the characteristic of the input impedance, the input impedance is a function of frequency, maxes out at R. Okay, and then add over the square root of 2, right? So 0.707 R goes across, that's that line, and we're going to say from here to here, this is my bandwidth. Okay, so it's nice to see on in a plot, but actually calculating it's not as well. It is kind of straightforward, but it's just not as easy to see. So we're going to talk about from this circuit and this design, what is Zn? My characteristic and my input impedance. That is just 1 over R plus 1 over J omega L plus J omega C, and this is the inverse. Any of you that had me for Pekka know I do not like doing that inverse stuff, but it's nice for doing this specifically, just to show you what it looks like. I don't really care for doing that whole inverse thing. But it works for this. So we're going to go with what's our input power. Let's go through this, and that is just my 1/2 VI complex conjugate. And going through this from your textbook, that's 1/2 my input impedance times I squared. Okay, and then that also equals 1/2 V squared 1 over Zn complex conjugate. Okay, we got to remember that we're always looking at, when we're replacing this I, that the complex conjugate actually matters. We have to carry that through the rest of the equation. Okay, so when we're doing this, this equals, and we can just say 1/2 this 1 over Zn, and we're just going to plug that in there, or right in here. I'm going to take this and plug this right in here, and since it's 1 over Z complex, we would just fix this as the complex conjugate and replace this and swap out these positives and negatives. So this ends up being 1/2 V squared times 1 over R. Okay, so we're still real. Plus, and this J was in the denominator, now I'm putting in the numerator and swapping the signs, so this ends up being J over omega L, and then minus J omega C, and there's no inverse because I don't need to do that. So we're going through this, and of course we still want to know what the power loss is, and that's when everything is purely real. So my power loss is equal to 1/2 V squared over R, and again, purely real. My work, based on the average magnetic and energy in the inductor and the capacitor, let's make sure we write this out. Wm equals 1/4 I of the inductor squared times L, which is your inductance, which equals 1/4 V squared 1 over omega squared L. And this is the current in the inductor. And then our electric field has 1/4 V squared C, and that C is the charge for the capacitor. Our power in is therefore our P loss plus 2J omega Wm minus We. So we're going to take the difference. And our Zn is now 2Pn over I squared. And again, you can go through and replace and swap this stuff out and make it look cleaner. But for the most part, the part that we're worried about is what is our characteristic, our input impedance when we want this to be purely real. And so this ends up being our input impedance equals P loss over 1/2 I squared, and this is equal to R. And again, our frequency, our resonant frequency is just 1 over square root of LC. Again, the same answer in the end. So, we are getting a little more information. You might be able to use some of this for some hand calculations, but there are other important factors that we need to worry about when we talk about circuit design and how we design for series, parallel, or the consequences of any design that you're using in microwave engineering. Probably one of the more frustrating things about microwave engineering is that anything you do to this circuit affects all of the circuit. So putting a trace on your board in a random location or routing from one side to the other that gets a little close to anything microwave signal strength can affect everything else on that line. And by the act of you trying to fix that, rerouting the trace, running it somewhere else, can affect other parts of your microwave design. So it's a constant battle between fixing and optimizing your designs to work the best that they can. You should never go for a design that is perfect. It's never going to get there. But trying to get something better is always a good choice. So one of the things that we need to worry about, and that's used in microwave engineering in order to know whether you're getting anywhere close to what you need it to be, is this idea of a quality factor. Okay, now this is this Q term, and you'll see it in your textbook, and it has a frequency component in, so it's a function of frequency. And there is this average energy stored over your energy loss. Okay? And this is energy loss per second. So it's basically the measurement of loss in a circuit. We want to know how much we're losing in this whole circuit. So looking at this shows lower loss equals higher Q. well, higher Q value. Okay, so looking at the Q value can give you some insights into the design. Your resonator losses are from, you get the conductor, your dielectric, radiation, heat. And all of this is represented by R. Okay, so that's kind of where we just lump all of that together. Anything that has a permanent loss, we lump together with R. Let's define some other terms. The Q factor for a resonator, okay, without any loading, is Q naught. So that is your unloaded Q. So if you want to use a term for it, it's called unloaded Q. Okay. We will go through series and parallel circuits for how this behaves and how Q factors show up in both of these designs.